We've been talking about differentiation and how to tell if a function is differentiable and what that means. And we defined a derivative as this limit where we took the slope of the secant line and we took the limit as h goes to 0 so that the space between the 2 points goes to 0. So we end up with the slope of the tangent line. So we have this derivative here that is represents the slope of the tangent line. Now, it's really key to find these derivatives to be able to analyze things like instantaneous rates of change and different things like that, especially in the sciences. We use these a lot, physics and things like that. But it's very cumbersome to have to calculate out this limit every time. So mathematicians have found lots of ways to calculate derivatives that are much quicker and easier. Now, you need to know this limit definition. This right here is an absolute must for you to know, to understand, to grasp, but we're not going to use it for calculating derivatives very much at all anymore. You need to have a formula page from this lesson or put it on a card, one of your cards in your spiral, because we're going to go over a lot of different formula type things. And in your book, they have proofs of all of these and how they derive these formulas. We're not going to go through those because I expect you to actually read those in your book. And I'm just going to give you some examples and things like that. So these are rules of differentiation. So basically, this is the easier way to calculate derivatives. So the first rule, this starts on page 112 in your book, is the derivative with respect to x of a constant is always 0. So if we have, for example, if we want to take the derivative of the number 7, we get 0. This makes perfect sense because what's the derivative? It's the slope of a tangent line. What's a function that's just a number? Well, that's a horizontal line. What's the slope of a horizontal line? 0. So that should be pretty clear. Draw you out a picture if you need to help figure that one out, if you need some help. The second rule deals with exponents. If we have a function that is x to some raised to some number, then the way you take the derivative is you bring the exponent down and then lower the exponent by 1. So for example, if we want to take the derivative with respect to x of x to the 5th, that would just be 5x to the 4th. Now you have to be careful. If we want to take the derivative of x to the negative 2nd, that would be negative 2x to the negative 3rd, because we're subtracting 1 there. So make sure you pay attention to that. This is really useful when you have functions that have the term in the bottom there, and we remember our negative exponent rules, so make sure you've got those. Now, if you have you want to take the derivative of a constant times some function, that means that you take the constant and multiply it times the derivative of that function. So, for example, if we want to take the derivative of 4x squared, then we have that constant times, and then we use this power rule here, bring the exponent down, and then lower it by 1. So you just get 8x. The next rule talks about what happens when you have two functions multiplied or added or subtracted together. I'm just going to skip one there. Alright, so we've got, if we want to take the derivative of two functions and they're either added or subtracted together, you can split it up and take the derivative of the individual ones and then add or subtract. So, for example, if you want to take the derivative of a polynomial, like this one, then we can take the derivative of each individual piece using the rules that we've already learned. Remember, this just means we're taking the derivative with respect to x. So the derivative of a constant is 0, plus, use that power rule, multiply by that constant out front, and then power rule for that one too. Bring the 1 down, and then it's to the 0 power, which is just 1. So your answer is just 14x plus 9. Now, remember, a derivative can be a function if you're looking at a general term for the slope of the tangent line for the whole curve. Each individual x value can be plugged in here. Like if we're looking at this is a parabola, remember? If we look on this parabola at specifically, say, x equals 0, then we can use this here, and we know that the slope of the tangent line at x equals 0 is 9, because we just plug in x equals 0. So most of the time we're going to get function values for the derivatives, and then we'll go in and evaluate it at specific places. All right, another rule is when we have two functions multiplied by each other. This is called the product rule, and you need to make sure you know this one because it's not quite as obvious. So when you're taking the derivative of two things multiplied, you take the first times the derivative of the second plus the second times the derivative of the first. So let me show you what I mean by that. Let's say we have this function h, and it's the square root of x times x to the fourth plus 3. Well, we've got this function here multiplied by this one here. So the way we can figure out the derivative, or h prime, you can write that as h prime, or you can write it as dh dx, or any of those. You take the first function times the derivative of the second. So this one we're going to use our power rule, and we're going to use that sum rule. So we'll have 4x cubed plus 0, so we don't need that, plus, and then the second times the derivative of the first. Now, how are we going to find the derivative of this? Well, remember, the square root of x equals x to the 1/2 power, so we can use our power rule to find its derivative. So we just take the power down and then subtract 1, and 1/2 minus 1 is -1/2. So we end up with this first times the derivative of the second plus second times the derivative of the first. Make sure you're good with that, and then you simplify. So x to the 3/2 power and x to the third power. Remember, when you have two things with the same base multiplied together, you add their exponents. So 3 is the same thing as 6/2 plus 1/2 is 7/2. And then plus, and then you can multiply this here. 1/2 times x, and then this one, add the exponents, so we have 8/2 minus 1/2, which is 7/2, and then plus, multiply this, 3/2 x to the -1/2. And when you simplify that, these have the same x, so we're going to add those together. So that's 8/2 plus 1/2 times x to the 7/2 plus 3/2 x to the -1/2. Now, most of the time when you have these, you're going to end up simplifying it. I'm just going to go ahead and show you through simplifying just to make sure you remember these things. I'm okay with leaving it right here, but when you take the exam, for example, and they have multiple choice questions, you may have to kind of look back and see how to simplify it further so you can get where they are. So if we have this, we have 9x to the 7/2 is all over 2 plus 3 over 2 times x to the 1/2, because it's this negative power, so it goes at the bottom. So if we want to get a common denominator, we have to multiply this times x to the 1/2 over x to the 1/2. We end up with 9x to the 4th plus 3 all over 2 times the square root of x. Or you can leave that as x to the 1/2, either way. But the point is this product rule right here. First times the derivative of the second plus second times the derivative of the first. Now there's one other, the product rule you're going to have to really make sure you memorize, and this quotient rule also, because they're just not quite as obvious. So when you want to take the derivative of the quotient of two functions, so u divided by v, it's bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. That's the rule. So for example, if I want to take the derivative with respect to x of x plus 1 over x squared minus 2, so I take the bottom times the derivative of the top. So what's the derivative of the top? Well, we take this exponent down 1, and then we have x to the 0, so that's just 1, and then plus 0, so that's just 1, minus top times the derivative of the bottom. So we use our power rule, and then the constant is 0, so leave that, and then we have all over the bottom squared. And we're going to, of course, simplify this down. We just keep simplifying until we get it where we need it to be. So we have negative x squared plus 2x plus 2 all over x squared minus 2 squared. And that doesn't factor anything, so that's not going to help you. So there's your rules. Now the book gives you a rule 7, which is a power rule, but for negative exponents. And it's exactly the same thing. We already talked about that. So you can look at that again. But basically what they're just reminding you that is if you have a function with a negative exponent, then when you take its derivative, you bring the power down and then subtract. Okay, so you just have to be careful like we talked about a few minutes ago. Now, those rules, like I said, you want them all on your cards. The 5 and 6, the power product and quotient rules, those you're going to have to memorize because they're not quite as obvious. So make sure you know those. Now, the thing about derivatives is you can take more than one derivative. So if you have, for example, this polynomial, you can take the derivative of this. We'll use that power rule and use the fact that a constant is 0, the derivative of a constant is 0. Now, this gives you the slope of the tangent lines for this function here, the instantaneous rate of change of the function. So for example, if this is a position function, then this gives you the velocity, because velocity is the instantaneous rate of change of the position. Now, you can take a second derivative, and you just keep going, same way, power rule. Now, this is the rate of change of the derivative. So it's this, if you graphed this derivative function, then this would be the slope of the tangent lines of the derivative. Now, what does that tell you? In our example here, if this is a position function, the rate of change of the position is the velocity. Well, what's the rate of change of velocity? Well, that's acceleration. So this would be an acceleration function if this started out as a position function. So this tells you where you're going, and this tells you your speed that you're going there, and this tells you how fast you're accelerating as you're moving along. Now you can keep going and take a third order derivative, and you get 336x to the 5th, and I believe that's called a jerk in this case. Like when you jerk on something, it's the change in the acceleration. And then you can keep going. Now once you get up to the past the third derivative, instead of using the little prime numbers, you use a number there with in the parentheses, and you just keep going with the same thing. And you could keep going. You could take a fifth derivative and a sixth derivative and so on and so forth. Just remember that these are the slope of the tangent lines of the one before them. So, like the jerk is how much the acceleration changes. And these are just, this is an example. It's not for everything. But if you start with a position function, its first derivative, the rate of change of the position is the velocity, then the rate of change of the velocity is acceleration, and so on, so that you get down to, so you can analyze what's going on with different products. Cars, they look at all kinds of different things when they're figuring out if the car is aerodynamic and that kind of thing. They use these derivatives and such to figure out all the stuff with the position and velocity, acceleration, all those kinds of things, so that they can understand what's going on with the cars, chemical reactions, and just any kind of motion at all, any kind of friction, work, all those kinds of things. They all rely on these various derivatives. So you need to make sure that you know how to deal with from one derivative to the next, how to get from one to the next and what they mean. You also need to make sure you're looking at these graphs and figuring out how they relate to each other. We'll go over that some in class and some more specifics about the ways that we use these Newton's laws and things like that. We'll look at some of that in class. Make sure you've read this section thoroughly. Make sure you've added things to that spiral card to study and have looked over those things. Like I said, these are new ways to compute derivatives, and all those rules will help you compute these derivatives, whether it's the first derivative, second derivative, third derivative, and so on. But you've got to make sure that at their core, they're from that limit. So read in your book, make sure you understand how we get all those rules based on the limits that the derivative gets its definition from. So make sure you've got that read. Make sure you got some notes, questions written down, so we can go over that stuff in class.